Okay, let's take roll. All right, that's a few names, please. Alejo Legares Adrian,
Here.
Alejo Legares Justin,
Here.
Vinny,
Here.
Francois, Boots,
Here.
Himes, Hodges. Oh, Himes is here. Hodges is here. David, Lee.
Here.
Momberg is here. Martin,
Here. Oh, Pete.
Hmm?
I was in a car accident last week on Wednesday, and that's why I wasn't here currently on Thursday.
what's your last name?
Martin,
Oh, okay.
I was in the Zoom, so I don't know if you saw me.
All right, I'll have to check and see. Melina is here. Moreno. Peluche. Summons. Wheeler,
Here.
White. And Zaragoza,
Here.
and Mr. David just walked in. All right, so before I start, your first test, which according to the syllabus should be given this week, I'm going to put it off until next Thursday, right? So you may want to make a note of this. I'm going to announce it in Canvas also. That it will be, the exact date will be, I just wrote it down here, September 18th, all right? So that test will cover chapters 1 and 2. All right. So basically what we're discussing will not be in that test. And I'll say more about it, but basically, it's going to be 3 questions, and you have to do all questions. And the only thing you're going to need to bring is a pen and a calculator. I'll provide everything else for you, including the tables. All right, the same packet that I've posted in Canvas. I'm going to bring copies of that to the test for you guys to use. All right,
Sir,
yes,
did I
sir.
hear that clearly? How many questions?
3.
Okay.
And you're to do all of them. All right. Okay, so that's pretty much all I have to say about the test. What I'll try to do, because I think I've graded test, not test, assignment number 1 for you guys. I have to grade assignment number 2. So I'm going to do that as soon as possible and get that sent to you ASAP so that you can use that to review for your test. And I'm going to also post the answer keys for both assignments as well, so that you can use that to help you to review. I think I'll be able to post some past test keys as well. So I'll do that later, all right? So if you review all those, then you should be in good shape to do well in your first test, all right? Okay, so with that, oh, you have a question? Oh, all right. So with that said, we're going to, let me show this. We're going to continue our discussion of chapter 3. And if I remember correctly, we did this question, right? The first example, did we? All right, so we didn't do this one. What I'm going to do is copy and paste this Word document. Okay, so that's a question. So this question says, it's talking about a compound known as diethylene glycol, which is used in antifreeze, and give some other uses. But the important part of this question was the data they gave us the composition, 45.27% carbon, 9.50% hydrogen, and 45.23% oxygen by mass. And you're to determine the empirical formula, all right? So, let me turn on. Okay, oops. Okay, so again, as in the previous example, I like to do this in a tabular fashion. Right? So again, as I said, with respect to the previous example, that if you're given percentage data to do problems like these, then you assume that you're working with 100 grams of the substance, which means that these values would represent the mass in grams for every 100 grams of the substance. So for the masses of the different elements, I'm going to put 45.27% for the carbon. I'm going to put 9.50% for the hydrogen, and I'm going to put 45.23% for the oxygen. And then we need to find the moles, and if you remember what we did, was that we take each of the masses. Oh, by the way, made a mistake here. It should be grams in each case. So this should be grams, and grams. All right. So as I was saying, to convert from grams to moles, we multiply each of them by 1 mole over their respective molar masses. So in the case of carbon, that will be 12.41 grams per mole. In the case of hydrogen, we multiply by 1 mole over 1.008 grams. And in the case of oxygen, that will be 45.23 grams multiplied by 1 mole over 16.00 grams. And then we need to do the calculation. So now, in the case of carbon, that would be 45.27 divided by 121.1. So according to my calculation, this works out to be equal to 3.769 moles, all right? And then we do the same thing for the hydrogen, 9.50 divided by 1.008. And that gives 9.42 moles. And then finally, 45.23 divided by 16. And according to this calculation, I got 2.87 moles, all right? Okay, now can somebody remind me of what the next step would be based on what we did in the previous example?
Divide by the lowest.
Right, you identify which of these would be of the lowest value and divide right through by that value. Each of these moles by that value. So the lowest is this one right here, right? So we're going to divide right through by 2.827 moles. So this will be 3.769 moles. 3.769 moles divided by 2.827 moles. Here we're going to have 9.42 moles divided by 2.827 moles. And this divided by itself will give you 1, right? So let's do for carbon first, 3.769 divided by 2.87. And according to my calculation, this gives you 1.333. And then in the case of the hydrogen, it's 9.42 divided by 2.827. And according to my calculation, that gives you 3.332. All right. So here we have a situation at this stage where the moles, or I should say not the mole, but the ratio, where you divide the moles of each of these by the lowest value, you're going to get a number which is not exactly near to an integer as we saw in the previous example, right? If you remember from the previous example, when we got to this stage, I don't remember what the numbers were, but they were close to an integer. If that's the case, then you round off to that nearest integer. But in this case, you cannot do that, right? 1.33, for example, is too far from 1 or 2 round off to an integer, right? So basically what we need to do now is to multiply right through at this stage by a certain integer, which will convert each of these numbers to one that is more closer to an integer, right? And you can get a hint as to what you should multiply by looking at what happens after the decimal point. In this case, you'll notice that there's a recurring 3 after the decimal point. So whenever you have a recurring 3 after the decimal point, what you can do is, here is create another line. And then you multiply that by 3, right? So 1.333 times 3 gives you 3.999, which is very close to 4. And 3.332 times 3 gives you 9.996, which is very close to 10, right? So therefore, the empirical formula in this case would be C4H10. Oh, by the way, you need to multiply this by 3 as well. Good idea. So C4H10 over 3. And that's basically how that is done. All right. So there are some instances that you may end up in a situation like this, where at this stage you cannot simply round off. You'd have to multiply by a certain integer. Now, let's go down here and give you a little chart here. So basically, let's say at this stage you have a number which has a recurring 3 after the decimal point. Then what you do is multiply by 3 to get the nearest integer, right? So if you have a recurring 3, you multiply by 3. If you have a recurring 6 after the decimal point, 6 multiply by 3. If you have a 5 after the decimal point, you multiply by 2. If you have 2 5 after the decimal point, you multiply by 4. If you have say it again. If you have 7 5 after the decimal point, you multiply by 4. If you have a recurring 1, you multiply by 9, and those are the ones I can think of right now. Yeah, that's it, as far as I can see. Now, in other cases, basically you have to do a trial and error thing, right? You have to try different numbers, multiply right through, and see if the result would be that the numbers that you end up with are close to integers, all right? So that's basically what you have to do in situations other than what I've just described here and here, right? So that's basically how that question is done. All right, any questions about this one? Any questions? 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 Okay, so back to the 4 points, we go. All right, so what we have just looked at are some examples where we determine the empirical formula based on percent mass data. But what if you're asked to determine the molecular formula? Well, to do that, you're going to need some additional information. You're going to need the molar mass of the particular compound, because there's a relationship between the molecular formula for a compound and the empirical formula, right? It's a simple integer, okay? So for example, if you have an empirical formula of CH2, then that means that the molecular formula could be CH2 or C2H4, or any other formula where there's a 1-to-2 ratio between carbon and hydrogen, right? So basically what you'll find is that there is an integral relationship between the empirical formula and the molecular formula. So how do we find the molecular formula? Well, what we do is we take the molecular formula mass and divide it by the empirical formula mass, right? In other words, whatever the molecular formula is, you add up all the atomic masses, and you do the same thing for the empirical formula, and then you divide the molecular formula mass by the empirical formula mass, and that should give you an integer. And in some cases, in practice, you might get, again, a number which is close to an integer. So you might get something like a 2.99, basically when they run off to 3, right? And then what you do to get the molecular formula is that you multiply each of the subscript in the empirical formula by that number, by the integral factor, and that will give you the molecular formula for the compound. So for example, if you're given this question, they gave you the empirical formula for hydroquinone, which is this, and they gave you the molecular mass, which is this, and the question is asking for the molecular formula. Basically, what you have to do first is find the empirical formula mass, And that would be equal to 3 times, based on the empirical formula that is, that would be equal to 3 times 12.01 AMU plus 3 times 1.008 AMU plus 16.00 AMU. And we work that out. Okay, so according to my calculations, this works out to be equal to 55.05 AMU. All right, so that's the empirical formula. And they gave you, or I should say, that's the empirical formula mass. And they gave you the molecular mass as being equal to 110 AMU. So therefore, the integral factor will be equal to 55.05 AMU divided by 110. No, I'm sorry, it should be the other way around. Let me erase this here. So it should be 110 AMU divided by the 55.05 AMU. And let me see what that gives. 110 divided by 55.05. So according to my calculation, this works out to be equal to when rounded up to 2 sig figs, this will be equal to 2.0, but remember it should be an integer, so that will be equal to 2. So therefore, the molecular formula that will be equal to C3H3O, and then multiply that by 2, so that will be equal to C6H12O2. And oh, sorry, I get another error on my part. This should be 3, not 6. I'm gonna worry about 6. So this should be 3. So that means that this is not 12, it should be 6. So that would be it. All right. Okay, any question about this one? Any question? Any questions? All right, okay, now here's something that I don't think you would have been introduced to in your introductory chemistry, because we just did some examples where we looked at using percent composition data to determine the empirical formula. So you might be wondering, how do we get these percent data values? Okay, so what I'm about to get into is what is called elemental analysis. And I'm going to describe a method here, which is how we get the data that we looked at in the previous example, right? Now, let me just say that this method here is one that applies to simple organic compounds. Now, I don't know if you know what the term organic means in chemistry, but organic chemistry is basically that area of chemistry which deals with the compounds of carbon, right? And most compounds of carbon will contain carbon and hydrogen, and in some cases oxygen. In a lot of cases oxygen, right? And it may contain some other elements as well, right? This method that we're describing can be used for compounds that contain carbon, hydrogen, and maybe oxygen if oxygen is present, all right? So basically what is done to such compounds is that we burn the compound in oxygen. And what you should have learned in your introductory chemistry is that if you burn any organic compound, then, and if you do the combustion, that's what we call burning in chemistry, combustion. If you do the combustion completely, then the products will be carbon dioxide and water, right? So that's basically what you need to remember. So the products of the combustion are carbon dioxide and water. So if you can find some way of trapping the carbon dioxide and the water that is produced and weigh it, then you can work backwards to determine what the empirical form of the compound is based on the masses of the carbon dioxide and water that is produced. So how do we get those masses? So this diagram here is basically a schematic representation of the setup, the experimental setup for this type of analysis, right? So let me just describe the different parts here. So here we have one compartment, which is the furnace. This is where your sample will be burnt, right? And then when the sample is burnt, as I said before, the products will be carbon dioxide and water, right? So the carbon dioxide and water will be guided into the next compartment, which contains a substance which will be able to absorb the water that is produced, right? So magnesium perchlorate is one such substance, and there's another one which I don't remember right now, but let's stick with magnesium perchlorate. So what's going to happen is that the magnesium perchlorate is going to absorb the water. Now, what you have to ensure in this setup is that you have enough of the magnesium perchlorate there to absorb all the water. You don't want any water escaping into the other compartment, right? So basically, you're going to have enough there. So what you should do in setting up this experiment, well, one thing I missed, I should have mentioned here, you need to weigh the mass of this original, right? And then when you get to here, you need to weigh this mass as well. And you need to weigh the mass of the sodium hydroxide. I'm going to describe that as well, right? So basically, once the water is absorbed by the magnesium perchlorate, the only thing that should be emerging from here would be the carbon dioxide, right? And the carbon dioxide will be guided into the next compartment where it's going to react with the sodium hydroxide, right? So basically, the magnesium perchlorate will absorb the water, the sodium hydroxide will absorb the carbon dioxide, right? And then you separate the different compartments. You take the mass of the perchlorate before and after. The difference between the two will give you the mass of water, right? You do the same thing with the sodium hydroxide. You weigh the sodium hydroxide before, and then you weigh it after. The difference between the two will give you the mass of the carbon dioxide, right? So that's how you get the masses of each of them. And then based on these masses, you can determine, and also based on the mass of the original compound, you can determine what the empirical formula of the compound is, right? So the next slide is basically an example of this type of problem, but I want to show you the diagram first so that you understand what the experimental setup is like, all right? So yeah, this is just telling us what I just said in terms of what is happening at each stage. All right. Oh, and this is basically using a simple example of methanol, right? If you burn it, so this is oxygen right here, then what will happen is that you're going to get carbon dioxide, and based on the balance equation here, you're going to end up with, for every 2 moles of methanol, you're going to end up with 2 moles of carbon dioxide and 2 moles of water, and then you're going to have some unreacted oxygen, which would be the excess reactant. And once you get the masses of these two, then you can work backwards to determine the mass of the methanol that you started off with, right? So that's a simple example, but we can apply this to more complex organic molecules. So here is a good example of a problem of this type. So let me copy and paste this onto Word. Oh, it's in Word. Let me get rid of all this here. Now, let me just warn you that this is going to be kind of long and protracted, but very important that you understand how to do these kinds of problems. Okay, so let's go back up here. So the question says, burning a 0.100 gram sample of a carbon, hydrogen, oxygen compound in oxygen yields and gives you the masses of carbon dioxide and water. And then it says a separate experiment shows that the molecular mass of the compound is 90 AMU. So they're asking for 3 things. A, determine the mass percent composition. So basically the percentage of each element present in the compound. B, the empirical formula. And C, the molecular formula for the compound, all right? So let's start off with A. So in the case of A, all right, so what you're going to do is you're going to start off with the given mass of carbon dioxide. Based on the mass of carbon dioxide, what you're going to do is find the mass of carbon in the carbon dioxide. And because the carbon dioxide is the result of burning the compound, that means that whatever the mass of carbon dioxide, whatever the mass of carbon in carbon dioxide is, will be the same as the mass of carbon in the original compound. All right, so we're going to start off with 0.1953 grams of carbon dioxide. And the first step would be to convert from grams to moles. So I'm going to put 1 mole of carbon dioxide above And down here, I'm gonna put the molar mass of carbon dioxide, which is 44.01 grams of carbon dioxide, all right? So this will go with this, and then the next step is to find the moles of carbon. So basically, based on the formula here, 1 mole of carbon dioxide will be down here, and 1 mole of carbon would be above, right? So far, we would have determined the mass of carbon present in the 0.1953 grams of carbon dioxide. But we're not finished yet, because what we need is the mass of the carbon. So we need another conversion factor, which would be how you convert from moles of carbon to grams of carbon, in other words, the molar mass. So the molar mass of carbon is 12.01 grams of carbon over 1 mole of carbon. And then we work this out. So let's see what this gives. 0.1953 times, or divided by 44.41 times 12.41. And according to my calculation, this works out equal to 0.053, how many six fifths? 4 6 fifths. So 0.05329, 0.05329 grams of carbon. All right. So that's basically how we get the mass of carbon. And that mass of carbon would be the mass of carbon that was in the original sample, right? Because all the carbon from the original sample is in the carbon dioxide that is produced when you burn it. All right. The next step is to find the mass of hydrogen. So, not me, I'm sorry. So I'm going to start off with 0.100 grams of water, right? That's how we're going to find the mass of hydrogen, right? So just like we did in the previous line right here, we're going to convert the grams of hydrogen, the grams of water to moles. So that means that we're going to need 1 mole of H2O as a numerator, and down here the molar mass, which is 18.02 grams of H2O. So that this will cancel out with this. Now the next step is where students very often make a mistake, right? The next step is to find the moles of hydrogen present in the moles of water, right? If you look at the formula here, right, you see that for every mole of water, there are 2 moles of hydrogen, right? So the next conversion factor here is 2 moles of hydrogen over 1 mole of water. I can't tell you how many times I've graded assignments and tests where at this stage, students put 1 mole here, right? So please make a note of it. It should be 2 moles of hydrogen over 1 mole of water, all right? So that this will go with this, right? So the next step, just like we did here, is to find the mass of hydrogen. So that means we need to multiply by the molar mass of hydrogen, which is 1.008 grams of hydrogen above, and below in the numerator would be almost put 2, 1 mole of hydrogen, all right? And then we do the number crunching, 0.100 divided by 18.02 times 2 times 1.008. So according to my calculation, this gives you 0.0, okay, again, 4 6 fifths, so 0.01119 grams of hydrogen, all right? So far, we have calculated the mass of carbon present in your original compound and the mass of hydrogen present in your original compound. But remember, the question says the compound contains what? Carbon, hydrogen, and oxygen. So here's my question to you. How would you, based on the information provided, determine the mass of oxygen? Mass of oxygen. We are already on the mass of the carbon. We have the mass of the hydrogen. So how would you determine the mass of the oxygen?
It gives us the mass, some 0.1, so we can subtract those 2 values.
Exactly. They gave you the mass of the original sample, right? Which is 0.1000 grams. And you subtract from that the sum of those two. So that will be the sum of 0.05329 grams plus 0.01119 grams for the hydrogen. So let's see what that gives. I'm going to work out what's within the parentheses first. And please, folks, do these calculations with me because I could be wrong. So please feel free to correct me if I made a mistake, all right? Okay. Okay, so this is what I got. 0.03552 grams. Right? Did you get that? Okay, so now we have the masses of all the elements present in the compound, right? We have the mass of the oxygen, we have the mass of the carbon and the hydrogen. So what I'm gonna do next is something that I did before. I'm gonna set up a table again. All right, so the first row would be where I will record the masses that we just calculated. So the mass of carbon was 0.0539 grams. The mass of the hydrogen is 0.01119 grams, and the mass of the oxygen is 0.03552 grams. All right, so you guys should be able to tell me what's the next step based on the examples that we looked at. What's the next step, folks? Convert to moles. Exactly. So we take the 0.05329 grams and we convert that to moles by dividing by 12.01 grams. We do the same thing for the hydrogen. 1 mole divided by 1.008 grams. And then we do the same for okay, so let's see what we get in each case. So starting with the carbon, that will be 0.05329 divided by 12.01 and rounded off to 4 sig figs would give us, according to my calculation, 4.437 times 10 to the minus 3 moles. All right. And then we do the same thing for the hydrogen, 0.0119 divided by 1.008, and according to my calculation, I got 0.01181 moles. And then in the case of oxygen, that would be 0.03552 divided by 16. And according to my calculation, rounded off to 4 sig figs, I got 2.220 times 10 to the minus 3. Let me do this again. 0.03552 divided by 16. Okay, that's what I got. All right. So those are the mole values at this stage, right? What's the next step?
Divide by the smallest one.
Okay, so divide by which one is the smallest of these here? Nope. Nope, it's the oxygen. 2.220 times 10 to the minus 3 is lower than. Right. So you're going to divide it right through by 2.220 times 10 to the minus 3 moles, right? So you're going to have 4.437 times 10 to the minus 3 moles divided by 2.220 times 10 to the minus 3 moles. And then here you're going to have 0.01181 moles divided by 2.220 times 10 to the minus 3 moles. And this divided by itself will give you 1, right? So let's see what each of these would give. So 4.437 divided by 2.220 times 10 to the minus 3. And according to, oh, something is wrong here. I did something wrong. Let me do this again. 4.437 times 10 to the minus 3 divided by 2.220 times 10 to the minus 3. That looks more like it. I got rounded off to 4 sig figs, 1.999, and then 0.01181 divided by 2.220 times 10 to the minus 3, and do a second. 0.01181 divided by 2.220 times 10 to the minus 3. Let me check something, give me 1 second, 1011. Okay. Okay, I'm in an error here. So I need you guys to correct me. So for this part here, this should be equal to 0.01110, which means that this here should also be 0.01110. Okay, let's see moles. Right, so let's see what that gives. So 0.01110 divided by 2.22 times 10⁻3. There you go. So that would give you 5.000. So therefore, this can be approximated to 2. This will be approximated to 5. So therefore, the empirical formula would be C2H5O. And that's, oh, that is the, all right. So admittedly, this is a relatively long solution to the question being asked. And in fact, we only answered the A part so far, right? But this is basically what you have to do, right? So let me stress again the importance of this part here. I can't tell you how many times I've seen this error. Remember, when you're calculating the mass of the hydrogen, make sure that the conversion factor that you use here is 2 moles of hydrogen over 1 mole of water, right? Very important, all right? Okay, any questions about what we have done so far for the, oh, actually we have answered the A and B part. Oh, we didn't answer the A part exactly. The A part is actually easy because all we have to do is find the percentage by dividing each of these masses by the original mass. So let me do that now. I'm sorry, I should have done that first. So the percentage of carbon would be the mass of the carbon, which is 0.05329 grams, divided by the mass of the compound, which was 0.1000 grams, times 100%. All right. So that would be equal to 53.29%. All right. And basically do the same thing for the hydrogen. The percentage of hydrogen would be equal to the mass of the hydrogen, which is 0.01119 grams, divided by the same 0.1000 grams times 100%. And that would be equal to 1, 2, 3 again, 11.19 grams. And let me see if I have some space down here I can work with. And then to get the percentage of oxygen, what was the mass of oxygen? 0.03552. So percentage of oxygen is equal to 0.03552 divided by 0.1000 grams times 100%. And 1, 2. Okay, so that would be 35.52%, right? And just do a quick check, the percentages should add up to 100%, right? So 53.29 plus 11.19 plus 35.52, and I got exactly 100%. So I'm fairly confident about the correctness of those numbers. So what I just did just now is to answer the A part of the question, and the B part is what I did before, which was to determine the empirical formula, which is this. All right, so please make a note of that. Now, the next question is asking for the molecular formula. So the empirical formula is C2H5O, right? That's the empirical formula, right? So the question is asking for the molecular formula. So if you remember in the examples, let me just clear some of this here. Okay, so if you remember the example that I did in the PowerPoint, remember I said that the integral factor is equal to the molar mass divided by the empirical formula mass, right? So they gave you the molecular mass, which is the same thing numerically as the molar mass. So that would be 90 grams per mole divided by the empirical formula mass. Now, how do we get the empirical formula mass? We add up the molar masses of all the elements in the empirical formula. So that's 2 times 12.41 plus 5 times 1.008 plus oxygen, which is 16. So 45.06 grams per mole would be the empirical formula mass. So 90 divided by 45.06 gives you 1.997, which works out to be 2. So therefore, the molecular formula for this compound would be the empirical formula mass, which is C2H5O, and then you multiply that by 2, so that becomes C4H10O2. And that's basically how that is done. All right? Any questions about this one? Any questions? All right. Any questions out there in Zoom? Okay, I'll take your silence to mean that you completely understand what we're discussing. All right, so continuing our trek through chapter 3. Okay, so again, this will be a bit of a review. Chemical equations. I'm quite sure we're all familiar with chemical equations. Chemical equation is basically a shortened way of describing a reaction, right? So instead of using words and sentences to describe a reaction, we use chemical equations. And of course, in a chemical equation, you have the reactants on the left side of the arrow, the products on the right side. The formulas are given, and in some cases, the states are given, meaning whether or not you're dealing with solids, liquid, gases, or aqueous, right? You might be given some additional information, like for example, a small triangle here, which means that you have heat to the reactants, not for the products. In some cases, you might be given actual conditions, right? So you could be given the actual temperature, you could be given, pressure, whatever, all right? So, some additional information sometimes is provided just to let you know exactly the reaction conditions, all right? Now, when it comes to equations representing quantitatively what is happening, we have to ensure that the equation is balanced. What that means is that the number of reactants, number of atoms of each element in the reactants must be equal to the number of atoms of those same elements in the products, right? And this, of course, is to satisfy the conservation of mass law, all right? So in the case of this reaction here, where you have hydrogen reacting with oxygen to form water, obviously this equation is not balanced, right? Because you have 2 oxygen atoms represented here, you have only 1 represented here, right? So the question is, how do we ensure that the equation is balanced? Well, the first 2 lines here are showing you what you should not do, right? One thing you cannot do in order to balance an equation is simply add enough atoms to achieve that balance to either side, right? That is a no-no when it comes to balancing equation. Another thing that you cannot do is change the actual formula of any of the substances involved, again, in order to achieve that balance, right? What you should do is make changes to what we call the coefficients, right? The coefficients are the numbers, the integers that are placed in front of the formulas for these different substances. So in this particular case, what was done was that because you have 2 oxygens here and 1 here, a coefficient of 2 is placed in front of the water, right? But because that 2 now affects the hydrogen here, where you end up with 4 hydrogens on the right, now you have to put a 2 here so that you end up with 4 hydrogens as well on the left, right? And therefore, this would be the correct way of balancing a chemical equation, right? So basically, to balance an equation, you do not simply just add atoms to either side to balance any particular atom. You do not change the structure or the formula of any of the substances involved. The only changes that you need to make would be the changes in the coefficients. And in a lot of cases, doing that is sort of a trial and error kind of thing, because sometimes what you do is that you put a coefficient in front of, let's say, a formula, and that would affect things on the other side, and you may have to erase some of those coefficients and replace with other coefficients and so on. So, as I said before, this is something that you guys should have practice with in terms of balancing equations, all right? Okay, so this is just some guidelines. I'm just going to go through these quickly. If an element is present in just one compound on each side of the equation, try balancing that element first. Balance any reactants or products that exist as a free element last. In some reactions, certain groupings of atoms, such as polyatomic ions, remain unchanged. In such cases, treat these groupings as a unit. And at times, an equation may be balanced by first using a fractional coefficient. The fraction is then cleared by multiplying each coefficient by a common factor. So let's look at these examples here. So the first one, how would you balance that equation?
Iron, 3 oxygen.
Okay, that's a start.
Four iron, 3 oxygen.
Oh, there you go.
Two,
Okay, hold on, let me change it. All right, so you're saying one now?
4 iron, 3 oxygen. Two of the finished product.
Okay, that's it. Very good. What about the next one? What?
2 C2H6. 3 O2.
You're saying put a 2 here
Yes.
and put a 3 here?
Yes.
Okay, so that 2 will make this 4 carbons, right? But we have 1 here.
One, yeah, you're right. 1 C2H6.
Okay,
And 2 CO2.
okay, so you're saying put 2 here for the CO2.
Yes.
Okay. What about the hydrogen? How would you balance the hydrogen? We have 6 here, and we have 2 here.
H6 plus two,
Hold on 1 minute. So you're saying what?
so 7O2 instead of 3.
Oh, 7. Okay.
Um,
Let's see if that works.
Two is still in CO2 and 3 in H2.
Hold on 1 minute. So 7 here, right?
Yes,
And then what?
3 H2O.
Okay, and that I think is correct. 2 carbons, 6 hydrogens, 14. Hold on, 2 fours. Okay, I don't think the oxygen is correct, hold on. Yeah, 4 plus 3, 7. So this is what I would do in this case. I would put, because this is 14. I would put 7/2 here to make that 7. Right? And then multiply the entire equation by 2 to convert this to an integer, right? So the final answer is going to be 2 C2H6 plus 7O2 to give 4 CO2 plus 6 H2O. And that should be the final answer. Because we're gonna have 4 carbons here, 4 carbons here, 2 times 6, 12 hydrogens, 6 times 2, 12 hydrogens, 7 times 2, 14 oxygens, and you're gonna have 8 plus 6, 14 oxygens. So the equation is now balanced. Right? That's a funny t-shirt. Okay. Wish I thought of that. Okay, next equation. How will you balance the next equation?
Three NaCN,
Okay,
3 HCN.
okay. That's pretty much it. Excuse me. That's it, right? Because now you have 3 hydrogens on both sides. Now this here, you can treat this as one unit. The PO4, that's phosphate. You have one of those on both sides. You have 3 sodiums here and here. And you have 3, again, this can be treated as one unit. You have 3 cyanides here and 3 cyanides here. So that's basically it as far as that is concerned. Okay, so I take it you all understand what's happening here. All right, so of course, the reason why it's important that you know how to balance equations because of stoichiometry, which is the area in chemistry which deals with quantitative relationships between different substances in a balanced equation. So that's what this chapter is all about. So before we can do any stoichiometric problems, you need to know how to balance equation because you could be given a question where you're given an equation which is not balanced, and you cannot do anything with it until the equation is balanced. So important when it comes to determining or doing stoichiometric problems. You need to identify what is called the stoichiometric factor, or the term that I prefer, the mole ratio, which is the ratio between 2 substances involved in a chemical reaction according to their coefficients, right? So if you get a reaction like this, carbon monoxide reacting with hydrogen to form methanol, then you can see based on the balance equation, mole ratio relationships between any 2 of the substances involved in the reaction. So as stated here, 1 mole of carbon monoxide is equivalent to 2 moles of hydrogen because you have a 1 to 2 mole ratio between those 2. You can also see that 1 mole of carbon monoxide is equivalent, chemically speaking, to 1 mole of methanol, again, because their coefficients are 1 and 1. And then finally, 2 moles of hydrogen would be equivalent to 1 mole of methanol, again, because it's based on the coefficients. So basically, it's very important that you need to have a balanced equation so that you can establish the mole ratios that you're going to use when it comes to particular types of stoichiometric calculations. So each of these relationships can be described as a mole ratio, a conversion factor, which is shown here in each case. So for example, the ratio between the moles of carbon monoxide and the moles of hydrogen as reflected in the balance equation would be 1 mole of CO2 divided by 2 moles of hydrogen when represented as a conversion factor. And you can also flip this around. It all depends on the type of question that you're dealing with and what kind of solution you're trying to achieve, all right? Now, the important step when it comes to these problems is, of course, the mole ratio. So you have to establish the mole ratio based on the balance equation. Once you get the mole ratio, then you can do that, use that mole ratio to carry the conversion, as you can see here. So if you want to convert the moles of substance A to moles of substance B, you'll have to multiply by this mole ratio, this conversion factor, which is 1 mole, which is the moles of B divided by the moles of A, all right? So this is basically the key step in any of the solution of these types of problems, right? And please note that there may be some preliminary or follow-up calculations that you have to carry out in order to answer the question that you're given, all right? So let's look at this particular example. This is a relatively simple example, especially since they gave us the balance equation already, right? So this question says that 0.105 moles of propane, which is this right here, is burned in excess of oxygen. So the question is asking how many moles of oxygen are consumed. So basically, you're going to start off with 0.105 moles of the propane. And you have to ask yourself the question, how would I convert from moles of propane to moles of oxygen based on the balance equation? And if you look at this equation here, you see that the coefficient for the propane is understood to be 1 here, and here it is 5. So the way you set it up here in this equation is 5 moles of oxygen above and 1 mole of propane below, right? And then you do the number crunching, this will go with that. So 0.105 times 5. So according to my calculation, this works out to be equal to 0.525 moles of oxygen. All right, and that's basically how that is done. All right. Any questions over this one? Any questions? Questions? Okay, so this is basically an outline of how to solve a stoichiometric type problems. And to be perfectly honest, the questions can come in many ways, right? It all depends on the information given. So you could be given a question where you're given a balance equation and you're given the mass of substance A, right? And then you want to find let's say the grams of substance B, right? So what you do first is you convert the grams of A to moles of A by dividing by the molar mass, and that will give you the moles of A. And then you use the conversion factor based on the coefficients of the two substances involved in the balance equation. So to get from A to B, in terms of moles, you multiply by this right here, moles of B divided by moles of A. Once you get the moles of B, again, depending on what the question is asking for, the question might be asking for the mass in grams, in which case you're going to multiply the moles of B by its molar mass, and that will give you the mass in grams, all right? And this is just one way of tackling a problem of this type. Again, it all depends on how the question is asked, all right? Now this is a question being asked. It says if we're given moles of substance A, oh, so what they're saying, what they're asking is, if you're given the moles of substance A, do we need to convert A to grams? What do you think? No, because once you get the moles, all you have to do is take it to the next step to get the moles of B, right? You don't need to convert to grams. You don't need to convert moles of A to grams in order to get moles of B, all right? Okay, so that's just a question that you're asking. Okay, so, all right, we should be able to do at least one of these questions here. So this is an example. It says the final step in the production of nitric acid involves the reaction of nitrogen dioxide with water. It also says nitrogen monoxide is also produced. So the question is asking, how many grams of nitric acid are produced for every 100 grams of NO2 that reacts? Let me copy this here and paste it onto Word. Okay. Alright, so the question basically is describing the equation in words. And it's asking for you to determine the mass of nitric acid produced, alright? Given that you're starting off with 100 grams of nitrogen, for every 100 grams of nitrogen dioxide that reacts. Okay, so let me ask you a question. What do you think would be your very first step in solving this problem? Yes, sir.
Writing the equation down.
Right, so you need to write the equation out. So based on the information provided, what I will do first is determine what the reactants are and what the products are, right? So let's see what clues we can get from the question. It says that the final step of production of nitric acid, so nitric acid is a product, right? So let me put the arrow here. I'm gonna put HNO3, right? That's a product. So that goes on the right side. It says involves the reaction of nitrogen dioxide. So nitrogen dioxide is a reactant, right? And water, right? So nitrogen dioxide and water are the reactants. The question also says that nitrogen monoxide is also produced. So I'm going to put NO over here, right? And that's it as far as reactants and products are concerned. So the next step is to balance it. So how do we go about balancing this equation? What's the first, what would you do to balance this equation? Yes, sir. I'm sorry?
One thing I'm seeing is there's H2O and then there's HNO3. Right, it's on the other side.
So you're saying put 2 here? Okay, let's go with that for now. Anything else we need to do? Well, that 2 that you place here will also affect the nitrogen, right? So let's see what would happen if we put a 2 here, right? Okay, anything else we need to do? What about the oxygens? We have 4 plus 1, 5. We have 2 times 3, 6 plus. Okay, now here's the thing. The nitrogens, actually I made a mistake. Let me erase this right here. Because we have 2 nitrogens on the left, on the right side. So I'll put a 2 here. Huh?
I think I got it.
Okay.
I got 3 nitrogen dioxide,
Oh, 3 NO2?
3 NO2. Plus 1 H2O,
Uh-huh. And what?
2 HNO3,
Uh-huh.
and 1 NO.
Okay, let's see here. So 3 nitrogens, 2 plus 1, 3, 6 plus 1, 7, 2, 3, 6 plus 1, 7 oxygens, 2 hydrogen. Okay, yes, so this equation is balanced. All right, very good. Okay, so now that we have the balanced equation, we can proceed to the next step, where you're given 100 grams of NO2, and you're asked to find out the mass of HNO3 that is produced based on this reaction, right? So I'll start off with 100.0 grams of NO2, and the first thing I will do is convert that to moles. So I'm going to put 1 mole of NO2 above, and then the molar mass of NO2. So nitrogen is 14 plus oxygen, which is 16. I'm sorry, nitrogen is 14.01 plus oxygen, which is 16, but there are 2 of them. So I got here 46.01 grams of NO2. So that would be how we get from grams of NO2 to moles of NO2. Now the next step is where we look at the mole ratio between the NO2 and the nitric acid, right? And you can see clearly that there's a coefficient of 2 there, a coefficient of 3 there. So up here, I'm going to put 2 moles of HNO3, and downstairs, I'm going to put 3 moles of NO2. So that this goes with that, All right? And then now the next step is to go from the moles of nitric acid to grams of nitric acid. So down here, I'm gonna put 1 mole of HNO3. And up here, I'm gonna put the molar mass. So for nitric acid, that's 3 times 16 plus 14.01 plus 1.008. So according to my calculation, the molar mass of nitric acid is 63.02 grams of HNO3. And then we do the number crunching. Okay, so 100 divided by 46.01 times 2 divided by 3 times 63.02. Okay, so according to my calculation, and please correct me again if I'm wrong, but I got 91.46 so 91.31 grams of nitric acid will be produced. And that's how that is done, all right? Okay, any questions on this one? Any questions? Any questions? All right, I'm going to stop here for today. And next class, I'm going to pick up with the next question here. All right, so that's it for today. We'll see you guys on Thursday. Yeah.
Okay, the Thursday or the next?
I'm sorry?
Did you say this week or next?
Next week,
Okay.
yeah. Chapters 1 and 2.
What lab are we doing today?
You're doing the dilution.
Pairing and diluting solution?
Yeah.
To do those steps.
Or, slap, that's why I'm on different, here, I have it on. More maps,
Okay, you sure this is calculated correctly? The molar mass, remember, we have to take into account the 5 more.
yeah, I put in a water ball for the one. That's where it's. Right, double.
Yeah, double check it, I will double check it. Okay, so that's number 1. I will just make this easy, so fine.
If I put zero, I'll set it, that I need help on that. Forget it. Around it.
Okay, so in case of 3. Okay, pretty much you're going to use the same equation. You're going to multiply the 10 mils by the 0.015 and divide it by the molarity, which is 0.10, the original molarity.
Set out one more time.
You're going to multiply the 10.
Yeah.
And the 0.015. Actually, it's very similar to what you did, what you done for number 2.
Oh, really?
Yeah.
It's just the same thing?
Same, the only difference is this right here, the 0.015 instead of 0.050.
Okay.
So just multiply 10 by that.
Yeah.
Divide by 0.1, and that will give you the volume of mils. And
So, like-
make sure you record it to 2 figures.
So like,
10 times 0.1, right, divided by 0.1, right.
all right, thank you so much.
All right?
I see what's left.
Yes, sir.
I was thinking for the, tidbits.
Oh! How could I forget? Should have checked the CD. What's the last name? Oh, you're the person who called me, right?
Yes.
Yes, I need to, I've not a chance yet, I I called the lady, she didn't respond until today. Yeah, you're here, okay. So, she said that I need to go into the system and change it. I didn't know that I could change it after the deadline. And then, I need to report it to my chair. And I don't know what happens after that, I don't know how long it takes for them to correct that issue. But,
Appreciate it.
yeah, no problem. I'm gonna do it while the life is going on, so that it can be done today.
Thank you.
Yeah, no problem. Okay, you guys out there in Zoom, I'm signing